So, as the title suggests, I will be talking about explainable reinforcement learning from an energy management perspective. But before I start delving deep into how we get explainability, let me share the motivation behind this research work, where currently we are seeing a lot of different things happening, especially in our power grids, where we are seeing a lot of electrification, especially the residential side, where a lot of EVs are getting added into the grid. A lot of people are shifting to heat pumps. There's also rooftop solar PVs that are getting added at a unprecedented rate almost. And this kind of combination or this increased dependence on a lot of intermittent sources, both on the generation side as well as on the consumption side, has led to a need for clean balancing resources, where system operators everywhere are facing this trouble that how do we balance the grid but use clean energy sources to actually balance it instead of fast gas-based turbines. And I think while this is a problem for a lot of system operators, it's also an opportunity in some sense, where we can now start again, or in a more specific manner, start looking at demand side energy flexibility, and especially look at areas like residential, which are sort of often ignored, but they do have the potential in terms of how much energy they consume. And so my problem or my research area or this paper generally focuses on this residential sector, where we know that it has the potential to some way contribute for demand side energy flexibility, but we also see that there isn't a lot of stuff happening, especially on a large scale, where we are still missing out on commercial products or large scale integration of residential energy flexibility. And like I see on this slide, there are many problems, but the two most important ones are that we actually need a control framework that is really scalable, where we cannot just work with optimizing a single house or maybe two houses, but we need to really expand it to thousands, 100,000 households to make like a meaningful impact. And we need a control framework that can actually do that. And secondly, if we're trying to go towards this large number of houses, we also want our end users to accept whatever solution we give. So if we come up with any form of control strategy, they should be on board and they should readily accept this strategy. And the first part, generally in research, we kind of blindly or maybe not blindly go for a data-driven control there, where we say that, okay, we have this fancy new technique called reinforcement learning that can really scale, really work with pure data. It is model free. It can just use observed data, some form of sensor data that you have. And in some sense, that is true. It is a promising solution, and we see a lot of research papers that actually look at different configurations of RL and how you can use it to solve different form of residential energy management problems. But that promising stuff is only if we can address a few key issues. The one that is most important for this talk is the lack of explainability, or when we have an RL agent that's giving me a control policy, I should also be able to explain it, or I should be able to at least understand if it is going to give me a good action. And when it does not give me a good action, I should know, okay, this action I should not consider. And that is really the motivation why we did this work, where the idea was, okay, we know this problem exists, and how can we actually improve the explainability of our RL-based controllers that we can standard take from packages, but then add a layer of explainability to them. And what would that look like? So if I have to share or if I have to present a simple problem to you, imagine this, where you have a household, it could be your own house, where you have some solar PV installed, you have a residential battery that you have just bought, and your house is exposed to some varying prices or maybe a capacity tariff like what we have in Belgium. And you have these different components that are coming into your life because of push for IoT devices or some kind of policy push where you're getting rebates to just put solar PV on top of your house. But now, if you want to make the most out of it, you need a home energy management solution, or you need some controller that can actually look at these different things that you have. Maybe a different house has a different flexibility asset, and you want this home energy manager to actually consider that asset and then work to achieve a certain objective. The simplest one, as I show on the screen, is just minimize my energy cost. Just take into account all the kinds of tariffs that I'm exposed to, somehow use my flexibility asset and minimize the energy cost. And while this problem is straightforward, it is also a sequential decision-making problem. There's a lot of uncertainties involved where solar PV can have some stochasticity in it. The user behavior can have some different patterns or just some randomness into it. And I want to make a controller that can also accommodate for these, say, exogenous factors that come into picture. Now, if I have to solve this problem using a reinforcement learning method, the standard solution we see is, okay, put it as an MDP. You would put all your houses, rooftop, battery, whatever it is, into a block, which is the environment that you want your home energy manager, which is the agent, to interact with. The agent would look at certain things. So it would get a state value, which could be, say, the state of charge of your battery, or it could be the current price of the hour or time of day, whatever. And based on these observations, you want the agent to come up with a control action. So do I charge my battery for the next hour or not? Or do I heat my apartment for the next hour or not? Things like that. And with this interaction, your agent would also get that if it takes an action, it would get a new observation. And if this observation is a good one, it would get a good reward. If it is not, it won't. And these observations are kind of these interactions are the key in terms of learning a good policy, mostly by trial and error. And what we currently see is in this setup, the agent that would have, like I show in the figure, an actor critic combination or some form of neural networks, they are able to learn a good control policy at the end of these interactions. But then the black hole remains that, okay, even if I learn all the patterns that are there and I'm able to generate almost close to optimum control actions, it's still not easy to explain because I'm using a neural network. And there is no way I can actually, yeah, answer the question on why are you charging right now, because it's always going to be some nonlinear transformation of some states that you have. And essentially what we are trying to propose in this paper or in this work is, what if we add a layer on top of it, which would take care of these explanations. So we know, or we are assuming, that your agent can come up with a good policy and it can figure out from the data whatever patterns there are, and it can accumulate that knowledge. And now the question is, okay, can we transfer this knowledge into something that's much more simpler, that's something which is much more explainable, that I can actually tell a homeowner or I can expose it to a homeowner. And that's where the policy distillation setup comes into place, where policy distillation is quite a mature technique in ML, where we want to create the student agent that would essentially mimic my teacher. So it would try to learn from the teacher. The only caveat being, or what we want to add here, is we want the student to be an explainable architecture. So we don't want to rely on Shapley values or feature importances to tell my explainability. We want the architecture itself to be explainable. And how do we do that? We use this differentiable decision tree architecture because decision trees are kind of quite intuitive or easy to explain. So as you can see here, there is a simple decision tree that I've shown, where you have some inputs X that go into the tree. You have some decision nodes where at each decision node, you kind of want to find out two things. What is the feature that I want to select based on the input data that I have? And if I have this feature selected, at what level should I put the cut direction and decide to go left or right? Now that happens in a decision tree, but we want it to be differentiable so that we can use it with policy distillation or any other stochastic gradient descent techniques that we have. And so we, instead of representing it as crisp decisions, we would show it as probability values. So that's the first equation there, where for each decision node, we would say that, okay, instead of going left and right, we would call it a probability of going left and right. And it would be given by such an equation where the red parameters are essentially weights, or they are the tunable parameters of this model. Similarly, we would need leaves that would actually give us the control actions. So what do we do there? We want a control action, but we also want to accommodate for some form of gradient there. And to do that, we use a weight vector and we use softmax to actually say that, okay, each leaf is going to now give me a probability distribution over all actions in my action space. And with these two, let's say, building blocks of the decision tree, I can now start creating my tree, where I would go in a linear fashion. I need to build a tree, but I'll build it as a composition of branches that exist. So one of the branches, the red one that I've highlighted in the slide, and I can compute the probability for that branch by accumulating all the probabilities that I see through it. So it would be just a simple product of all the decision nodes that I encounter, and then the final leaf that we have. And I can do this for all the different branches that this tree can have, which will give me something like this, where it would be a final output, which is the probability distribution over my entire action space given an input X, and it's a combination of all the branches that I have. Now I can plug this in into my policy distillation setup, put a KL divergence or such thing, and train this differentiable decision tree, just like I would have trained a neural network based student. So this was the architecture that we proposed, and now let me take you through some of the results that we have uh, to kind of illustrate on, or the focus here was that we want to show if really this tree-based structure is explainable or not. So we consider a relatively simple problem or a simulator per se, which tries to represent the home energy management scenario that we see in Belgium, where we used some data from a colleague's house. We exposed it to Belpex prices. We had a battery installed, which is more or less typical of what we find in houses there, and we used a simple or more or less a standard algorithm, which is DQN, as our teacher algorithm to see if we can actually A, learn good policies, and B, if we can prove or if we can at least show that these policies that we get are explainable and can be exposed to users. Now, on the table, I show results in terms of the mean cost that my home energy management controllers get. And the only takeaway here is we did this experiment to basically benchmark that, okay, if we have this policy distillation set up and if we actually try to distill some information from a teacher, can the student policies do something meaningful, or can they at least come up with a control policy that is good enough? They would never be as better as they would never be better than the teacher, but are they in the ballpark at least? And these numbers kind of indicate that yes, there is some closeness, or they're close enough to the teacher agents to say that they can be deployed, or the trade-off is not that high. And they're of course doing better than the rule base, which is a sanity baseline that we have. But there is this discrepancy here where the DQN is still, the teachers are still doing better. And we also want to understand why this discrepancy might exist, or what's exactly the reason why the two would be different. And so to kind of check this thing, we try to visualize the control policies that we have. So it's a simple representation or a simple visualization where I'm plotting the control policy as a heat map. The colors would indicate what actions my agent is going to take. On the x-axis, you have the state of charge of the residential battery that you have, and on the y-axis, it's the normalized price, because we expect that the agent would look at price as a prominent feature. And as you can see, the bottom rows are the DQN-based agent, or it's my teacher agent, which is using neural networks to come up with a control policy, whereas the top row is actually the student network. And we can clearly see the difference that, okay, when we are using the neural network based agents, the policies looks a lot more complex. It has a lot more non-linearities in it. And whereas with the student model, it's a relatively simple policy. It's just cutting the grid into sections or regions, mostly rectangular, as we expect with a decision tree. The interesting part comes if we look more closely, where especially in the left-hand section, where there are portions of the policy map where your DQN agent might be taking some weird actions. So I've highlighted one which I thought was non-intuitive. And what's happening here is the DQN agent is actually saying, okay, you might be in a region where your price is low and your SOC might just be 50%, but I would still not charge. I don't know why. I as a human would have expected, okay, that's a good point to charge your battery. Later on, you can discharge it when the prices are high, and maybe you can make some money out of it. But that's not what we see from the DKL policy, and that's something which is always going to be tricky, because if you're a company who has deployed this in a household, and if a customer calls you and says, okay, why aren't you doing this? You cannot really answer them. And that's something which we can see is being solved, or it's at least being addressed by the differentiable decision tree agents. That's the top row, where we see a clear consistency or an intuitiveness to the control policies. Where, for example, the one that I highlight on the top right corner, we see that there is some clear separation of regions. We see that, okay, the agent is saying simple things where it's looking at SOC. If there is enough SOC and if the price is high enough, it would just discharge and try to make money out of it. Or alternatively, if the price is extremely low and if the battery is empty, it would just say that, okay, I need to charge it because I might need to use it later on, or I can arbitrage it in a future timestamp. And that's something which is much more intuitive, which is much more easier to explain to an end user. So while this is just a comparison, we can also, because we have a differentiable or because we have a decision tree based structure, we can also create a tree out of it, or we can create a rule set out of it, where we can essentially represent our policy as different branches of the tree. For example, this thing where instead of looking at a policy as a tree, you can just look at as a set of rules where if it is sunny and if the demand is high, then do something. If it is cloudy and if the demand is low, you can do something. This is one such example where we can see that, okay, the agent looks at solar PV and the non-flexible load of the house, and it decides some action which we can attribute later on to a peak shaving kind of a behavior. Or similarly, if we look at another branch of this tree, we can say that, okay, it's now looking at this particular control action from an energy arbitrage perspective. And we can actually question this policy as well. So I can really use it to even do a sanity check before deployment, that is my policy good enough or is my policy accurate enough. But I can also expose such a thing to a user and kind of explain it whenever they have a question or whenever they feel like my agent is doing something wrong or doing something strange. They can always come and see this kind of a graph or this kind of a rule set and be like, okay, maybe it makes sense, maybe it does not. And that's the advantage of using such a explainable structure, and that's what we had proposed. So to summarize, I think, well, I don't have a lot of time, but the key takeaway here was that if we want to at least introduce some form of explainability to our RL-based structures, the uh, a good way to go forward would be to actually try creating architectures which aid in this explainability. And in this work, we wanted to introduce this decision tree based architecture as one such method that we can use to have some form of explainability in our RL setup. And now, in terms of the future, we would try to expand our home energy management scenario where we can use heat pumps, we can use some form of thermal behavior as well, and see if these trees can actually cope up with it. And similarly, then go for a pilot demonstration or a proof of concept to start getting more users into the mix. Yeah, I would like to stop here. Thank you so much for listening. And if you have some questions. Okay. Yeah.
Okay, thank you for the presentation. I got two questions. First one, you said that you're using the student like architecture to learn like the teacher's ability. So two questions. First of all, how maybe it's a simple naive question. How do we know the student architecture that you pick has the ability to learn the teachers like what the teacher can teach?
Should I?
This is the first question.
Should I answer it? Right?
Sure.
Yeah, so that's a good one. And right now it was mostly based on intuition or some form of domain knowledge that we have, where we kind of expect that a decision tree or a simple set of rules, or like what I show in the heat map, where a simple rectangular division of the policy space can lead to a good control policy. That was an intuition or a domain knowledge that we had. And so we somehow expected that if we distill even from a deep neural network, we should be able to get a control policy that's doing good enough. Moving forward, there might be scenarios where it may not be possible, but then that possibility can be addressed by sort of tweaking a few things in the sense of how the rules are generated. Because at the end of the day, we do not want the most optimum solution anyway. We want the most explainable one. And so we can trade off at appropriate areas to still distill it into a rule-based structure. So that's
Okay, thank you. My second question is that can you go back to the slide where you showed the like the figure, like previous one?
Yeah.
Yes, this one. It seems to me the student is not learning the teacher's strategy. Is it?
So it's partially like your observation is partially correct. Indeed, from the figures, it looks like the student is not learning the teacher policy exactly. And the reason here is twofold. One is in terms of the distillation. Uh, what we are trying to do is we are trying to learn the entire distribution over actions, whereas the teacher policy that you see is just a greedy policy that we have. And so in this distillation step, we feel that because the student agent is trying to mimic the distribution of actions of the teacher and not just a single value, it's kind of learning something slightly different than the teacher policy. And that's why the discrepancies come into picture. The second is also that the student is way less expressive as compared to the teacher, where it just is made up of 4 or 5 rules. And because it's still gradient descent, it's trying to come up with a configuration of those rules that can best fit the teacher. And so in these scenarios, maybe it spent more time optimizing the first and the last column. And so the second column went completely bad. And that's just a artifact of low expressiveness that we are, say, forcing upon the architecture.
I see.
So,
So sorry.
Yeah.
Last quick question is did you get a chance to compare, directly ask the student to learn, but without the help of the teacher? Do you see any advantage there, or by using the teacher strategy as
Yes and no. So we did present yesterday where we learned the differentiable decision tree from scratch, and it works, but it's just difficult to train because it can easily go wrong. Or the whole aspect of reinforcement learning is you're doing a lot of trial and error, and you want your policy to be progressively learning something better and better. Whereas with teachers, if for example, if one of the features that I'm learning, if it just goes wrong, then the tree would end up in a really bad policy and it would start collecting data for that bad region of my space. And there is a good chance that it would never converge to a good value in terms of control policy. And that's something which we saw where the stability was really difficult to obtain. But if we were able to get stable agents, they were performing well. So that's also a part of our future work that we hopefully will be able to do.
Okay, thank you.
Question there.
So first of all, thank you very much for your nice presentation. I have one question to the slide before, where you compare the different policies. Couldn't you use the figure there to just explain the policy of the DQ network? So to just use this and then say, well, the DQN is also explainable?
We cannot, because this figure was artificially obtained where I had to actually fix the loads that I have or the net load of the house to these 3 values. And to create this, basically I had to dumb down my problem so that it would only have these 3 values as state inputs to the DQN agent and then visualize it. And whereas if I go to a different scenario where I have more than 3 or 4 features at play in my state, then I won't be able to come up with a good simplification to visualize policy maps. And that's actually the reason why we yet don't have a good technique of explaining RL policies.
Okay, thank you very much.
Yeah, thanks for the talk. That was great. I was just wondering, how do you see, like, as you incorporate, like you were mentioning, maybe in the future, incorporating more things into your state space, making it more complicated? How do you see the scaling working out with the explainability of decision trees? Like if you need to let the depth go higher and then it eventually gets less explainable?
Yeah. So that's one way where we just make 10 deep trees or something like that would hamper the explainability, or we can go to a different approach where we start dividing, or we start going into this hierarchical control regime where each asset still gets a shallow tree, which is explainable. But then I also need a top level agent that would just pick out assets and that can have its own explainable policy. And as long as they are connected via a common gradient, in principle they should work, but I'm pretty sure training them would be tougher. So that's something we are looking into.
Okay, cool. Thank you.
Hi, nice work. So I'm curious if you thought about essentially discretizing the action space for RL as well, because when you train the decision tree, you discretize the action space. Am I correct?
Yes,
because you have 5 actions, right? Do nothing, charge,
Yes.
charge halfway, and so on, right? So so that simplifies the problem to a great extent, right? So have you looked into discretizing the action space for your base models that are used for evaluation when you do this? Because that could help with both like explainability, and at the same time you may not lose that much performance in that case.
So we did look into discretizations, and also right now the teacher models are discretized to the same action space of 5. So the bottom graph also has a discrete action space of 5 elements. But I get your point, and over there, yes, it would make sense if we reduce the action space, that the policies might come interpretable. But the problem that I highlight here with this particular region, we aren't guaranteed that this level of discretization would solve it or not. Or if we just have 3 actions, we would still encounter such a problem. And with differentiable trees, what we want to do is to try to make it more intuitive and try to represent it in a better way. So that's the problem that we want to solve. Also, maybe a point to note here is neither of the teacher nor the student needs to be a discrete action based agent. They can also work with continuous. It's more of a choice from explainability perspective.
Take one last question.
Yes.
Okay, I'll make it quick. It's a bit of a follow-up with regards to the complexity. So you indicated that one way to battle complexity was to split basically into shallow models. So the XRL literature has a huge corpus on distilling into decision trees, either directly or by teacher-student learning, and they're all battling the complexity issues. So can you, especially when you're going towards more complex scenarios and using like SAC, which needs much more data to train on, right? Can you give a theoretical bound on which you, for example, split or on the complexity? Because pruning is a huge thing for all these approaches nowadays.
I cannot give a theoretical ground, but that's something which we also want to work on. But I like just commenting on the pruning part of things, because the work is deeply rooted in trying to make the models explainable. We have an intrinsic constraint that we want to keep the models as shallow as possible. And so the pruning aspect would happen more focused on explainability, or is my tree getting out of hand that I cannot explain it, and that's where I decide to draw the line, versus, or like that would be the decision instead of performance being the indicator for pruning that tree. So I think, but we can discuss it offline.
Yeah, exactly. Thank you.
Okay, so let's thank the speaker.